Hi everyone, and welcome to the second of 4 videos going through some past exam questions on lattice enthalpy. So here we've got another question. It looks very similar to the previous video. We've got all our enthalpy changes and the values here. But the first thing we've got to do this time is we've got our Born-Haber cycle, and it's saying in the boxes write the species present at each stage. So we've got to fill in the gaps basically. So let's have a look and see what's going on here. Here we've got solid potassium and we've got sulfur as a gas. We need something to go here, and at this point we've got potassium as a gas and as a positive ion. So two things have changed here. The potassium has changed into a gas and it's also become a positive ion. Okay, so we've got to only do one thing at a time. So what we should have here is that this needs to be the potassium just as a gas. We need to do that first because this process is the ionization energy, and you can only do that from gaseous atoms. So it must be a gas first before we can do the ionization energy. And you can see that the sulfur hasn't changed at all the way through this, so that's just going to stay as it is. Right, what's going on here? Actually, it's probably easiest to fill this in first because we can see what this process is going to be. This big negative process that ends up with potassium sulfide. This is our lattice enthalpy. And for a lattice enthalpy, it's the formation of 1 mole of a lattice from its gaseous ions. So this has got to be the gaseous potassium ions and the gaseous sulfide ions. And now that we've got that, that makes this one easy to fill in because we can again spot the difference. The potassium has stayed the same. Sulfur's gone from sulfur as a gas to sulfur 2-. So in the middle here, we need to have just a sulfur 1- and the 1 electron. Don't forget the electron here. Okay, these two stages are the first electron affinity and the second electron affinity. So it's just adding 1 electron at a time. You will lose a mark if you leave that off. Okay, and also make sure you've got all your state symbols as well. Okay. Right, moving on. What we then need to do is define lattice enthalpy, and I just said it 30 seconds ago, and I said in the first video on this topic, this question always comes up. We need to make sure we've got this definition. So it's the enthalpy change that accompanies the formation, can't write quick enough, of 1 mole of an ionic lattice from its gaseous ions. Okay. And then we need to calculate the lattice enthalpy. Okay. So for this one, we're going to do it the same method that I showed you in the first video. So first thing I want to do is go back to our diagram here, and I want to get these numbers on the diagram, just so we get them in the right places. So the enthalpy of formation is -381. So that is this here from the elements in their standard states. The first electron affinity, so that's these two processes here, isn't it? So the first electron affinity is this one, -200. And then your second electron affinity is that one. This is our lattice enthalpy we're trying to work out. The atomization of sulfur is +279. So that is going from sulfur as a solid to sulfur as a gas. That's this one here. The ionization energy of potassium is going from potassium as a gas to potassium ion as a gas. That's there. And then the atomization of potassium must be this one here. But again, we need to be careful because we've got K2S. So anything to do with the potassium needs to be times by 2. So again, go look back at this and go, right, where does it say of potassium? That's potassium sulfide, sulfur, 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 potassium. For ionization energy of potassium, 419. So that needs to be times by 2. And the atomization of potassium, +89. So this is going to need to be times by 2 as well. Then we want to do this one. So we're starting here. and we're ending here. So therefore we're going to have to go that way round. So we're going to go down there, up there, and then all the way down this side. And now we can use this to start doing our calculation. So what numbers do we have? We have plus 640. Remember we said we're just going to put these in brackets, then we're going to decide what to do with them afterwards. So I'm just going to run down these here. Well, actually, I'm going to do them in the order that I've got on here. So then we've got minus 200. We've got plus 419 times 2. We've got plus 89 times 2. And then I've got plus 279 and minus 381. Right, what are we then going to do with these numbers? Do you remember we said we're going to compare these arrows? Are they in the same direction or are they opposites? So here they're opposites, so we're doing the opposite process, so that needs to be negative. These two are opposites to each other, the way we're actually going and the way it should be. So we need to do minus that one. Opposite, 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 and then in the same direction for the last one. Okay. So this is the last one is the only one where we're going to put a plus sign on. So we're going to go minus, 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 and put a plus for the last one. Okay. And then this is the calculation that we're doing. So we're going to do minus 640, minus 200, so then plus 200, minus 419, minus 419, minus 89, minus 89, minus 279, and then plus minus 381, so that's going to be minus again. And we get minus 2116. That is a sensible value. We are expecting lattice enthalpy to be very negative, aren't we? Okay, so it seems reasonable. Right, final question in this one then. What have we got here? We've got some ionic radii. Predict the order of melting points for sodium bromide, potassium iodide, and rubidium chloride. Okay, so this is the idea that, well, actually, we can kind of go to the explanation first. Actually, I'm going to do this. The smaller the ionic radius, the higher the charge density. Because we've got the same charge. The charge is the same, it's just 1 plus and 1 minus. So the higher the charge density, because we've got the same charge spread over a smaller volume. The smaller the ionic radius, the higher the charge density, and the stronger the attraction between the ions. And then this question is not actually asking us about lattice enthalpy values, it's asking us about melting points. Well, they are linked, but let's talk about melting point. So if there's a stronger attraction between the ions, there's going to be a higher melting point, yeah? And the higher the melting point. So now we need to think about putting them in order. So let's look at the combinations. Let's look at let's compare the positive ions and let's compare the negative ions. So the best positive ion to use would be the sodium, right? That would be number 1. And then potassium would be number 2, rubidium would be number 3. And here the best negative ion to use would be chlorine, or chloride I should say, and then bromide, and then iodide. So if we've got sodium bromide, we've got the best positive ion, the smallest, and we've got the second best negative ion. With potassium iodide, we've got the second best positive ion, but the worst negative ion. Rubidium chloride, we've got the worst positive ion, but the best negative. So out of these three combinations, this is the best one, isn't it? Sodium bromide. So that's got that's the smallest kind of combination of ions. So that's going to have the highest melting point. And then rubidium chloride, we've got a 1 and a 3. And then the potassium iodide is going to be the lowest, because both of those are quite large. Okay. So we've said the smaller the radius, the higher the charge density, the stronger the attraction, the higher the melting point. So let's just say sodium bromide has ions with the smallest radii. And potassium iodide has ions with the highest radii. And then that links to what we've already said.